Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we'll go through box plots, also known as box and whisker plots. So these are statistical displays and they display what is known as the 5-number summary. We'll get to that in a second. So box plots always have this characteristic shape. They have a box like this, and it has a line through the middle, and then at each end they have these lines known as whiskers. That's where we get the name box and whisker plot. So they always have this characteristic shape. So as I said before, they display the 5-number summary. So the 5 numbers are known as Q0, Q1, Q2, Q3, and Q4. They're the numbers we need to create a box plot. So what do these numbers actually mean? So these are the 5 numbers that are displayed by a box plot. Q0 is the minimum, just the lowest score of your set of data. That's pretty easy. Q2 is just the normal median. You know how to figure that out. It's the middle score when there's an odd number of scores, or if the number of scores is even, you take the average of the 2 middle scores. Just like you've been doing since year 7, we're not calculating the median any differently. The maximum's really easy too. It's just the highest score in a set of data. So the things that are new are the first and third quartile. So to find the first quartile, what we're going to do is divide the data into a lower half and an upper half. The median of the lower half is the first quartile, and the median of the upper half is the third quartile, or Q3. So box plots essentially divide the data into 4 equal groups. So from the minimum to Q1 is supposed to be 25% of the data. I say supposed to be, it's not always exactly 25% of the scores, 25% of the data, but it's close enough. So between Q1, first quartile, and the median is another 25%. And then in this section between Q2 and Q3, another 25%. And then we have another 25%. So the top 25% of scores lie between Q3 and Q4. The lowest 25% of scores lie between Q0 and Q1. And then the middle 50% of scores are in this box here between Q1 and Q3. So it gives us an idea of the distribution of scores. So Q1 is the point at which 25% of scores were lower than it. Q3 is the point at which 25% of scores were higher than it. So it gives us a lot more information than if I just gave you a list of numbers. So I can tell a few things about this data from the box plot. So I know that the top 25% of scores were between 11 and 15, the middle 50% of scores were between 4 and 11, and the bottom 25% of scores were between 1 and 4. Now, one thing that I can't get just from looking at a box plot is the mean, because it doesn't tell us the sum of the scores or how many there are. So if I just give you the box plot of data, you can't tell what the mean is. You also can't tell what the mode is, because we don't know what the most common score is. The box plot just gives you these 5 things about the data. All right, now we're going to look at a set of data and turn it into a box plot. So let's say I have this set of data and I want to turn it into a box plot. So the first thing I need to do is put the data in order from smallest to largest, because I need that in order to calculate Q0, 1, 2, 3, and 4. So let's put it in order from smallest to largest. So now that I've put it in order from smallest to largest, I need to calculate the 5-number summary. So I need to calculate Q0, Q1, Q2, Q3, and Q4. So Q0 is really easy. It's just 7. It's the minimum. So Q4 is also really easy. It's the largest, so it's 15. So I'll calculate Q2 now, which is the median. So there are 10 scores here, an even number of scores, so there'll be 2 middle scores. So what I do is I divide the data in half. So I take the average of the 2 middle scores, 9 and 11, to calculate the median. So 9 plus 11 over 2 gives me 10. The median of this data is 10. So now I just need to calculate Q1, the first quartile, and Q3, the third quartile. So Q1 is the median of the lower half. So I've divided the data into lower half and upper half. So if I look just at the lower half of the data, I can see the median is 8. So Q1 is 8, it's the median of the lower half, and Q3, the median of the upper half, will be this number here, 13. 2 scores above it, 2 scores below it. So now I have enough information to draw a box plot. So I draw a number line like this. There's no need for me to start at 0. So Q0, the minimum is 7, so I put a little dash there. So remember, this is the whisker. The lowest 25% of scores are between 7 and 8. So I draw a line up to here at 8. So the box goes from Q1 all the way to Q3. So Q3 is 13. So I draw the box like this. This represents the middle 50% of scores. So I draw a line in the middle of the box for the median, which is Q2. And then I draw a whisker from Q3 all the way up to the maximum. So from 13 to 15. There we are. I've drawn my box plot. So another measure that's important when we're thinking of box plot is called the interquartile range, or IQR. So the interquartile range is sort of an alternative to the normal range. So you know, for this data, the normal range would just be the highest score minus the lowest score, 15 minus 8, which is 7. So the problem with the range is it's susceptible to outliers. If you have a few outliers, a few really large or really small numbers, it will make the range a lot bigger, and it might make you think the data is more spread out than it actually is. The interquartile range is just Q3 minus Q1. Tells you the difference between that middle 50% of the scores from this point to this point. That distance is the interquartile range. And so, like the range, it's a measure of spread, but it's not susceptible to outliers. If you have really large or really small observations that are sort of out of place, it won't affect the interquartile range heaps. It won't make it really, really large and make you think that there's a bigger spread than there is. So in our data here, the interquartile range is very simply Q3 minus Q1, which is 5. So you can see the interquartile range will always be less than or equal to the normal range. So now we're just going to draw a box plot where there are an odd number of scores. So please pause and copy this down if you need. So now I've given you a data set with 9 scores. So we're going to calculate the 5-number summary again. So once again, Q0 is really easy. It's just the minimum, which is 10. This time I've put the data in order for you. So Q2 is the normal median. So there are 9 scores. So the 5th one will be the middle, because there are 4 scores above it and 4 scores below. So the median of this data, Q2, is 24. Q4, the maximum, is 44. That's really easy to calculate. So once again, we need to calculate Q1 and Q3. So remember, to calculate Q1, we needed to divide the data in half. Well, I can't actually divide this in half because there are 9 scores, an odd number of scores. So what I do is I cross out the middle score and divide this as the lower half and this as the upper half. So I still take Q1 to be the median of the lower half. So the median of these 4 scores halfway between 19 and 20 is 19.5. And Q3, the median of the upper half, it'll be halfway between these scores, 27.5. So I'm going to turn that into a box plot in a second. But what I also need to discuss is the concept of outliers. So in previous years, we've heard the term outliers, and we've just viewed them as numbers much smaller or larger than the rest. We haven't had a definitive method for checking is a score an outlier or not. We've just looked at it and said, oh yeah, it's quite big, must be an outlier. So with box plots, there is a definitive way we're going to use to determine whether or not a score is an outlier. So we're going to look at our data now and decide whether or not there are any outliers. So from common sense point of view, we probably think 44 is an outlier, but we're going to definitively determine that. So a score constitutes an outlier if it's more than Q3, the third quartile, plus 1.5 times the interquartile range. So in our example here, the interquartile range is just 27.5 minus 19.5. Just Q3 minus Q1, which is of course 8. So a score will constitute an outlier if it's more than Q3 plus 1.5 times the interquartile range, which is 39.5. So any score above 39.5 constitutes an outlier. So of course that means 44 is considered an outlier. A score will also constitute an outlier if it's less than Q1, which is 19.5, minus 1.5 times the interquartile range. If you put that on your calculator, it's 7.5. So the number 10 does not constitute an outlier because it's not less than 7.5. So when we're plotting box plots, we usually don't include outliers in the box plot. We usually leave them outside the box plot and mark with an X. So I'll show you what I mean. So again, I label my number line. So I'm not going to include 44 in the box plot. What I'm do is I'm going to go to 44, estimate it here, and put an X. So now let's do the rest of the box plot. So 10 is the minimum. I include that in the box plot. It wasn't an outlier. So Q1, 19.5 is about here. You can just estimate. No point, measuring it precisely. So then Q2, the median was 24, which is about here. The box goes all the way to Q3, which was 27.5. Just like there. And then I'm going to draw a line, the whisker, to the next highest score, which was 29. So it's going to look like this. This is my box plot with an outlier here. It still has the same interpretation, so 25% of the scores, the lowest 25% of scores between 10 and 19.5, and then the middle 50% of the scores are displayed in the box and the top 25% outside the box. Again, it's not precise. It's not exactly 50% that are in the box. It's not exactly 25% here, but for all intents and purposes, it's close enough. All right, I just need to do one more example where we're looking more at the shape of box plots. So we're just going to have a quick review of the terms positively skewed, negatively skewed, and symmetrical. So I've drawn here 3 histograms for you. So for histograms, they always have F frequency along the vertical axis. So the higher the bars are, the more frequent, the more times those scores occurred. So along the x-axis, the horizontal axis is always the scores themselves, and they go from low on the left-hand side to high on the right-hand side. So the top histogram, this one here, is positively skewed because there are a higher frequency of scores closer to the minimum. Symmetrical histogram, you can see the highest frequency scores occur in the middle, and negatively skewed, the highest frequency scores occur over here, closest to the maximum, okay? So you have to be careful with this because it sort of goes in the opposite way that you'd expect. You'd expect positively skewed would have more high scores, but it's the opposite. It actually has more low scores. So what we're going to do is we're going to look at what would a box plot look like if the data it represents is positively skewed, symmetrical, or negatively skewed. So let's start with data that is positively skewed. So the box plot would look something like this. There'd be a small distance to the left-hand side and quite a long distance to the right-hand side. So why is that? Well, the median is here. So that means there are the same number of scores. There are 50% of scores in this little area here, and there are the same 50% of scores in this wide area here. So the only way that could happen is if there were a lot of scores clustered here in this 50%. There'd be a high frequency of low scores so that this distance contained the same number of scores as this distance. So predictably, if data is symmetrical, so too is its box plot. So this is what a symmetrical box plot would look like. It's the same in both directions, same distance. Okay, so that's roughly symmetrical. So negatively skewed would be the opposite of this one here. What would happen is there'd be a wide sort of range for the lower scores. And as you get larger, the box plot gets narrower like this, okay? So again, that's because from here, from the minimum to the median is 50% of scores in a wide range. And then from the median to the maximum is another 50%. So there are the same number of scores in this small area as in this large area. So scores would be clustered here. There'd be a high frequency of scores over this side closer to the maximum. All right, sorry for the long video. Thank you so much for tuning in. This has been the luckiest maths teacher in the world. Have a great day.